Electric fields and forces is what we're going to talk about today. And it all began with a kite. And you guys have heard the story about Benjamin Franklin and how he discovered electricity. He did a lot of stuff. So in 1752, Franklin set off a bunch of research in the field of electricity with his famous kite experiment. And really what he noticed was that as a storm blew in, that the string, the tether for his kite would seem to gather a charge, and then it would repel each other, the dangling strings. And so he really was interested in what could cause this. And so when he got shocked by this event, it really gave him something to think about. So we need to talk about electrical charges. There are two types of charge, a positive and a negative, and we can thank Benjamin Franklin for that. And like charges repel, and unlike charges attract. And charges are always conserved, and we've heard a lot of that in chemistry last year and in physics this year. So we know that energy is conserved, and this is just another form of energy. And charge is also quantized, and we'll talk a little bit more about that. So it just means we can calculate it. There's two kinds of charges, positive and negative, and it was really an arbitrary choice, but it really made a lot of sense once we started looking more into it. So if you had two balloons and you rubbed them together, what you would see is that they would push away from each other. They would repel one another. If you rub a balloon in your hair, what we see is that the hair and the balloon are attracted. Like charges repel and unlike charges attract. Since this is the fundamental rule of electricity, there must be two different things that are going on, a positive and negative. Again, it was arbitrary. So the two balloons, since they were the same type of substance, they would have the same charges built up, and so they would repel. Whereas when you use two different things, like a balloon and hair, the charges then are alike, and so they're going to attract. And anything that is electrically neutral has the same amount of positives and negatives, and that would give it the net charge of 0. So here again, like charges repel, unlike charges attract, and you can do this with all kinds of different materials. Two charged plastic rulers can repel. Two charged glass rods would repel each other. Again, they're the same. But if you took then the charged glass rod and the charged plastic ruler, they would attract. So electric charge is conserved. Since you have already been through chemistry, you know that electrons are what surrounds the atom's nucleus, and these are the things that are very mobile. And since things are made up of lots and lots of atoms, then we have lots and lots of electrons that can be rearranged. So when you rub two things together, electrons can be stripped and they could be moved among the substances. So if you're talking about your balloon and the hair, the balloon is stripping the electrons and becoming negatively charged, and since your hair lost it, it became positively charged. And if you remember from chemistry, we call those cations and anions. And this is an example of charging by friction. The positive charge of your hair is equal to the magnitude of the negative charge of the balloon, which is that conservation of electric charge. Electric charge is quantized, meaning that it occurs in discrete amounts, and so that's actually something you calculate. So charge, energy levels on atoms, photons, we can figure out what exactly is giving it the charge. The electron and the proton have equal but opposite charges. Kind of an interesting way to write it. The value has been experimentally determined to be 1.60 times 10 to the negative 19th coulombs, which is the SI unit for the electric charge. And this is a good number to know. We talked about that in chemistry as well. If you remember Millikan, he did an experiment that he could actually calculate the numbers and was able to get part of this as well. And there it goes. So he discovered the fact that the charge is quantized. There was always multiples of this number on those oil drops that he was able to make hover in his electric chamber with the oil drops. One of my favorite experiments. You can classify substances in terms of their ability to transfer these charges, and you've heard of these terms. So we have electrical conductors, which is stuff in which electrical charges move freely. You think about these as metals: silver, gold, copper, and aluminum. Most metals are conductors of electricity and heat. And then you think of electrical insulators, stuff in which the charges do not move freely. And this would be like glass and rubber, styrofoam, silk, plastic, pure water, things like that. We have a semiconductor, where something between an insulator and a conductor. And usually what that means is that the electrical charge can be moved over a very short distance and not the long distance like you would expect with a wire, which is why they're so good in computers. Superconductors, stuff that has no resistance to the electrical flow when they are at or above a certain temperature. And we just watched a movie in chemistry, and hopefully we'll get to watch it again when we get a little bit of time in physics, about absolute zero. So those of you that took chemistry last year or this year, hopefully you remember that video when they showed the supercooled materials act as superconductors. They have no resistance to flow of these electrons, and so they behave incredibly interestingly. Now, polarization, we've talked about this with light, and so, but it also applies. Polarization in light is when we line them up, the direction of the light, the photon waves, and we can make them go through barriers, and so we can polarize it, the concept behind polarized lenses and sunglasses. Polarization, when we talk about a charge, means when we have regions that have different charges, opposite charges. We saw this a lot in chemistry when we talk about ionic compounds, and we knew that like sodium is a positive charge and chlorine is a negative, and so we saw that. And when we build up charges, you can also have this, rain clouds do this. So an electrically neutral object may have regions of positive and negative charge, and then they're separated from each other, and so we call it polarized. It can experience an electrical force even though it has a net zero charge, because remember that it's balanced because they're equal and opposite, but then they're separated, which means that they can have a flow among the substance. And so bits of paper are neutral, but electrically charged rod polarizes paper and it tracks them. Then we've got a picture on the next page. And then we can say the paper is polarized by induction. When objects are charged by rubbing them against one each other, both electrons and the ions, the charged atoms, can be transferred from one object to another. You've noticed this probably around even Houston, is that when we drag our feet on carpet in dry weather, cold weather, we can make a lot better shocks than we can in really humid weather. But this school seems to be pretty dry. I seem to shock myself a lot here. Insulators are best charged by friction. Metals, they can move the charges around, so they don't hold the charge very well. Once an insulator is charged, the charge remains where it is. And so here's an example of how to charge like a ruler, and you can see it interact with the paper pieces. A ground, and you've heard of this, of grounding a circuit or plug in your wall. The earth is a conductor because it has lots of ions and moisture, and it's so big that if we will take a wire and lead it to ground, it will bleed off or pull off the excess charge and put it into the ground where it can be dispersed very nicely. To ground a conductor means to provide a conducting path between it and the earth. This would be also like a lightning rod. The round opening of a modern electrical outlet is called a ground. So this is that third extra metal part that comes out of a plug. Okay. So charging by induction is essentially charging an object by bringing another charged object nearby. So you can charge a rod and hold it near a conductor, and then ground the conductor, and the excess electrons will leave the rod, travel through the conductor and into the ground. And then as soon as you remove the ground, then it will hold the charge. Electrostatic force wins by a long shot. Gravitation is the weakest force. Electroweak force is like 10 to the 20 times stronger than gravity. That's 20 quintillion times stronger. A billion trillion times. Gravity and electrostatic forces are two completely different things, so it's like comparing apples to oranges. So the gravitational force is what it is, and the electric force was what it is, but they are going to behave a little bit the same, follow the same kind of rules. Gravitational forces only attract. Electrostatic forces can attract and repel. Gravitational forces cannot be shielded, but electrostatic forces can. Gravity depends on mass, where electric forces depends on charge. So, if you remember back a ways, the law of universal gravitation was the force of gravity, F sub g, is the gravitational constant times the masses of the two objects divided by the distance between them, r squared. Coulomb's law, which is the one we had mentioned before, is the force, and electrical force is the constant, which is going to be the Coulomb's constant, and the two charges of the two objects and the distance between. So here's an example. The electron, which has this mass, very, very tiny, and a proton of a hydrogen atom are separated on average by a distance of 5.3 times 10 to the negative 11th meters. Find the magnitude of the electrical force and the gravitational force that each particle exerts on each other. So we're just going to use that formula. We have the distance between them. We have two masses, and so we can just calculate then the forces that are between them. So here's the first one. So we plugged in the value for the gravitational constant, the two masses, and divide it by the distance between. And we get the force due to gravity is 3.6 times 10 to the minus 47th newtons. Very, very tiny. Okay. So we have the two charges. We have the constant, the Coulomb's constant, and we have the distance. So plug in those numbers. And we get 8.2 times 10 to the negative 8 newtons. Very straightforward. So hopefully this helped. We will practice it in class, and we'll also practice it with a worksheet. And if you have any questions, make sure you ask me. Thanks. Bye.
Have a good night.
Bye.